In this video, I'm going to explain why Henry's law is used in vapor-liquid equilibrium, and then show how we use Henry's constant to calculate concentrations in a liquid phase of a component that's present in low concentration. So I'm going to plot here fugacity of component 1 in solution, so the hat implies in solution, versus the mole fraction of component 1. So pure 1 is here, pure 2. So fugacity of pure component 1 is this value here. This is the pure component fugacity. When, of course, there's no 1, the fugacity is 0. If we have an ideal solution, then we expect just a linear relationship. We expect a straight line. This is what Raoult's law or the Lewis-Randall rule shows. Ideal solution is the straight line. Ideal solution says fugacity of component 1 in solution is just its mole fraction times its pure component fugacity. Now let's look at the case of a real solution, and let's look at a real solution with a positive deviation from Raoult's law, which means its fugacity is above this ideal value. So I've indicated an example of real solution showing positive deviation. For Henry's law, we're only interested in the low concentration regime. So low concentration of component 1, mostly component 2. And for Henry's law, what we're going to say is the fugacity at this low concentration is going to be x1 times some constant that we'll call Henry's constant. And so if we look at this plot and we draw a tangent at the low concentration, and what we're interested in is a straight line behavior. So this is h1. This is Henry's constant, and it's a function of both component 1 and component 2 because it's a function of their interactions. So we're only going to use it at the low concentrations where this is going to be a pretty good approximation. The question might be why we would use it at all. And what we're looking at is, suppose we have component 1 and we're way above its critical point, and we're only going to have low concentrations. For example, oxygen dissolved in water. We're not going to get the high concentrations. So we know Henry's constant, then we can calculate the fugacity by making this approximation that we're at low concentration. So H1, it depends on both 1 and 2. In other words, Henry's constant for oxygen dissolved in water is different for Henry's constant for oxygen dissolved in benzene. So I've indicated Henry's constant for oxygen dissolved in water. Units are bar. And notice for oxygen dissolved in benzene, it's a much smaller value. And then also shown for acetylene dissolved in water. So Henry's constant depends on both components. A higher Henry's constant then is going to correspond to a lower concentration in the liquid phase. Higher Henry's constant means a higher fugacity of the solute, a higher escaping tendency, for example, to go into the gas phase. So higher Henry's constant, lower concentration. Now we can use Henry's constants to calculate what the mole fraction would be, and we'll just look at a simple example here. So I've indicated the Henry's constant for oxygen and CO2 in water, and then at equilibrium, we're going to say the fugacity of oxygen in the vapor phase is equal to the fugacity of oxygen in the liquid phase. This means the mole fraction of oxygen times the total pressure. It's the partial pressure of oxygen. And in the Henry's regime, it's the mole fraction times the Henry's constant. So we're given that the partial pressure, 10 bar of oxygen, x1 times 44,250. And let's call this, so we don't get confused, x of oxygen. This is the Henry's constant of oxygen in water. So mole fraction of oxygen is quite small, 4.75 times 10 to the minus 5. And then the same calculations are shown for CO2 at 10 bar. Much smaller Henry's constant, so therefore a much higher concentration of CO2 in the liquid phase. Keep in mind, we're dealing with Henry's constant. We're talking about low concentrations of that component in the liquid phase so we can model it with Henry's law.